Hey there, my name is Kevin and I'm going to be talking today about the UAV that I developed as a capstone project for my control systems and embedded systems courses. This presentation is more focused towards the control aspect of the system, but if you're interested in the embedded systems development I did for this UAV, you can find the link to the presentation video below in the comments. So to get started, I had to find a project, and I wanted to stay in the aerospace realm because that's where my interests lie. And through other projects and internships, I've had the chance to work on rovers and rockets and some other things. So I wanted to do something that had a new set of dynamics and something that could increase my understanding of other types of systems. Component availability was important, needed to be available and relatively straightforward to obtain. Something that I could build on later was important as well. And as I mentioned previously, applicability to the embedded systems development project. So with that, a UAV was chosen because it was all of those things. And I decided to use the quadcopter instead of a fixed-wing aircraft just because it was easier in terms of my testing area to realize versus a fixed wing, which takes a lot bigger open space in order to fully test. So a little bit of the system dynamics and control used in my development was a decoupled linearization of the control of the axis and its motion, because a real thorough analysis, you will find that the dynamics of a quadcopter, because you're using the Earth reference frame as well as the body frame and trying to somehow combine those two, it's pretty math intensive. It involves state space models, Euler angles, nonlinear equations, and was just a little out of the scope of this project. Something very interesting to research further, but with the methodology that I used of decoupling the axes and using them as linear control, that provided just enough theoretical background to make the control happen. And then lastly, I decided to use PID control for the stability because it's a robust style of control that essentially, over various conditions, will provide the desired stability for the aircraft. And here you see the axes that I used and their definitions in terms of positive rotation, negative rotation. And now here you have the flowchart for the flight phase of the system. Again, if you are more interested in the embedded systems, there is more flowcharts and descriptions in the presentation for that part of the project, but here is more involved in the stability control. So we're going to take a look inside that black box, and there we go. So this pseudo flowchart block diagram wasn't intended to represent the system mathematically. What I wanted to show was signal end to end and its flow. So essentially the PWM voltage is what's actually supplying the motors their signal, which makes them turn at a certain rate, which provides a certain torque, which makes it turn at a certain rate, which gives a certain vertical lift, which combined into a specific axis gives the pitch and this so on and so on, all the way to the sensor, which reads that, then the values that it outputs, some of the filtering I did on those signals, into the, and this is actually all part of the feedback, into the PID controller. So there's PID controllers for each axis, and then they cascade out into a summation where they are added to the set point based off of a scaling gain factor. So eventually at the end, all of that control has been translated into the specific signal for each motor, each of the four extremities of the quadcopter body. But modeling this mathematically would have been very, very difficult and again out of scope of the project. So what I decided to do is instead focus on the PID control of one of the axes, the roll axis. So this is the control system block diagram for that axis, which, and in skipping all of the steps going from theta measured to theta out, all the way through all of the torques and rotations and angular velocities to thrust and whatever, just focusing on the control of the position. So a PID functions essentially by manipulating the error and a predictive and a past data-based style. So the proportional one is just a proportion of the error directly. So that responds to now. That will have a very fast response rate, but it will have a tendency to readjust a bunch of times because it has that fast response rate. So it'll overcompensate and overcompensate and overcompensate. So that on its own can be good for something that's a little more stable in terms of the system already. But for something that has such a really minor balance stability point, something that's a little bit more in depth was helpful. So the I part, what's nice about it is that it builds over time, right? So as the body frame gets turned, then until that body frame gets recorrected, it will continually send the correction value. So what it does is it has memory almost. So if you start here and you turn it here, it will send the control signal until it's rewrited. So that's using the past data. And then the D gain only sends a signal to the change of error. So if the error is 0, that's fine. And if it starts to turn, well, it'll create a signal that initially opposes that turn. But once it's starting to turn, it will keep turning, that's fine. So what it does is when the system starts to go out of its stable position, it will send a higher spike to try and keep it there, and then it'll leave the rest of the correction to the P and the I block. So that brief overview of the PID controller is feeding into the transfer function of the actual system. And I will elaborate that a little bit more on the next slide, but the rest of this system block diagram that you see here is the disturbances coming in, potentially gusts of air, various air density, and then we have the sensor that ultimately measures the angle and what has been produced from this control and sends it back to be summed with what we hope to have as our state of device. So this goes a little bit more into the actual finding of the transfer function for the system, and this wasn't something that I was as familiar with being in the mechanical world, so lots of research, lots of textbooks. I found this in a very cool article about modeling quadcopter dynamics, this transfer function here, so I figured that was a good thing to hold on to. And then I also ended up borrowing my wife's mechanical engineering control systems textbook. It's in French, but read it anyway. And that basically confirmed what I was thinking, that this is a second order and type 1 system, because we have the inertial, we have the moment of inertia from the frame itself, because it's a rotating system around the axis, around the roll axis. And then we have the drag of the propellers. And those are really the two only aspects of the system that need to be controlled. And so from that, we were able to find the generalized form of those systems. So the transfer function for the plant, or the actual physical system, the UAV, that is this. And then the PID transfer function in the S domain can be combined into this, with each of the gains for each of the types of control, excuse me, over S. So after the mathematical model was kind of discovered, developed, verified that it should be the appropriate model, it was imported into Simulink, and so I built that with various parameters for the gains and for the actual transfer function values, and it was behaving basically as I expected it to. So after that, that verified that even with the change in some of these values, the system response would be as appropriate and was being modeled correctly. Now, for actually defining the variables and the gains in the system, because I didn't have very much data on the transfer function of the physical system of the drone, there were some estimations used, as well as just some trial runs and tuning. So for the tuning of the PID, that was actually all done practically. So because I didn't have any way to measure the data coming back from the flights, I ended up just running the flight, testing its performance characteristics, and adjusting things in gradual steps until it provided a fairly stable flight pattern and stability control. So the variables ended up being defined here, and you can see the final transfer function for the PID. And then for the actual body and drag, the body was more clear on how to estimate, so I just took the mass of the system, made some general calculations of the length of each of the arms to the propellers, and that was used. But the drag was something that was really difficult to find or find how to calculate, coming from an electrical background. And many chapters of textbooks later, I decided that that could be something, in my simulations I use as contrasting things showing how the system responds differently, which was part of the goal for this project as well. So with that, I used a few different ratios of the moment of inertia to the drag to the overall system gain of these values here. So using the moment of inertia that I found, into these ratios, you have these two system transfer functions, transfer function A and transfer function B for the system. So after that, I did some time response analysis on these, and you see here on the top left the time response of the first transfer function A here, with the 1 to 20 ratio, and without the PID compensation. And although it's not terrible, it's a mechanical system, so there's a little bit of overshoot. It takes a little bit of time to be stable. We're trying to correct on a 4 millisecond time base, so a 4-second stability is just not possible or usable. So with that, after that has been corrected through the PID compensation, you can see that the response is much improved. The time base has gone down measures of magnitude, and the stability it obtains is very stable very quickly. And same thing shown for the second transfer function used, and so it seems like this transfer function that I had estimated was probably less likely to be accurate, as you can see by this time response in the oscillatory pattern. It eventually stabilized, but again, that oscillatory pattern is probably not representative of the real system. However, even with that crazy step response for the transfer function only, the system transfer function only, after it had been compensated by the PID controller, even that signal was very manageable in terms of time response, in terms of peak characteristics and overshoot. So it really shows the power of a PID controller or PID control algorithm in the system, given that the system is difficult to control in terms of when it's stable, it doesn't need much control, but as it turns, the control signal needed is much greater. So for the varying system characteristics, you can see that the response is still very manageable and acceptable. Again, for the same different transfer functions, version A and version B, we have the root locus plots. And here on the top left, I wanted to show a root locus plot again without the compensator, without the PID. And it's pretty straightforward. There's the pole on 0, and it's going to be stable for every value, which is great, but the response and where it looks to go for that stability is not obvious, not close. So it has the potential for a lot of oscillation, it has the potential for very slow response. And after the PID has been added, you can see that this is no longer the case. There are extra poles for each of these, or extra zeros, sorry, that each of these poles can find, and with that, a faster response time. In fact, so much so that I used the second transfer function to show this, because this one was the more unstable transfer function to start with, that if you zoom in, this little thing that you just see as a 0, there's actually another section here where the pole that's on right at the centroid of this graph can find this 0 right here, which is almost invisible here on the full zoomed out plot, but it really shows the response and that speed of finding that and getting the system into stability. And this is that same transfer function but zoomed out. And so here are the Bode plots for each of these different transfer functions. You can see that again, the first version is probably the better estimates of the ratio between the drag and the moment of inertia, which didn't make sense at first, but after a little bit of analysis, it made sense that because it's already mostly stable to start with, the quadcopter frame is, that any change would be probably more, the element that would affect the change more would be the drag of those rotors versus the actual moment of inertia on that center of the axis. Then you see the slightly more unstable transfer function to start with, slightly more unstable here, but overall still within good characteristics. So we're going to jump over here to YouTube now so we can enter this in full screen and see a little bit of the demos of the system. So we're going a little fast on the first sections because this was covered a little bit more in the embedded systems part, but there's the integration and calibration of all of the subsystems. I'm just going to jump ahead a little bit on these because, again, this is covered more in depth in the embedded systems section. But there's different phases of the program and the whole system. So there's the calibration and startup phase, there's the flight sequence, and then there's the ground phase until someone recovers and resets it. Again, jump ahead here. So this is me testing the system with just the P gain and seeing that the motors were adjusting and trying to compensate for the change body position as expected before I did more PID tuning. This is after I had tuned the PID controllers, and this, I was not actually holding it, I was just kind of acting as a guard next to it, so in case it started to do a corrective action very fast, I could maintain control of it, but that was all pretty much its own control. So this is the part that's a little bit more relevant in the control systems. So the battery's connected. I'm going to unmute this so we can hear it start up. So there's the beeps for its startup phase. Its blinking LED means that it's calibrating the ESCs, which control the speed, the RPMs of the propellers, and therefore the thrust and lift and balance of each, axis. And the system was designed to slowly step up in altitude until it reached a preset maximum, either height or time elapsed, and then slowly work itself back down. So you see its propellers increasing in speed until it reaches its takeoff thrust, when it comes forward and bumps into that thing. But notice there are multiple corrections of body position throughout flight. So the control algorithm is working. It's just the trim was off. It was a little too far forward. This one, same thing. I readjusted the trim and you see it take off. A couple control corrective actions. There's another couple of them. It's relatively stable, but as the trim is off, it's drifting to the right. And through the testing phase, because I was space limited, unfortunately I didn't have the time to go out to the big fields close by the edge of the city. The propellers got more dinged up and a little less balanced, and that brought the stability of the overall system down. And with that, the flights became slightly more unstable each time, but you can still see multiple corrective actions and steps taken from the PID control algorithm each time on the body. Now this flight, I actually think is probably the best example of the control algorithm, because even though the real time looks fairly unstable, you see in the slow-mo that it takes off. It's a little unstable, so there's the P part of the PID controller taking action, and now it's stable, but it's drifting a little bit, so it sees that it's drifting and starts to correct the drift, but then it catches its foot on the ground and ultimately spins out. But if you see that catch of the foot is really what spins it out overall, and I think if it had a little bit more space, it could have came about and corrected that drift. So we're going to watch it one more time So it takes off, it gets a little unstable, but it provides its correction that it's supposed to. It gets itself stable. It notices it's drifting, so it corrects and tries to drift back the other way, but it catches its foot and it's been gone. So it got to a point where the propellers were just being too dinged up to really have as balanced a flight as I was hoping for. So the goal of testing moved to having a successful full flight sequence from low thrust to high thrust, back down again, without crashing, which is what's demonstrated here. And you see it takes off, makes a couple controller corrections of its balance, and lands again. The propellers slow down until they come to a stop. So we'll jump back here to the presentation. So a few things that were learned in this exploration, development, and research was the first thing was the inability to capture the data from the real system was really limiting in the fact that the only response to the real system that I could compare with the simulations was the physical flight data that I was observing. And although that provided insight, and although I was able to adjust that programmatically and practically by adjusting the gains, adjusting the trim, it was less close to the theoretical modeling and calculations than I would have liked with this project, which was also limited by the way the Arduino interfaces with the computer. So every time you plug it back in, it restarts the program. So I was actually not able to pull flight data out, even if I was able to store it in the program. So at the bottom here, that mentions that I could have used system identification toolbox in MATLAB and done some data-based design and use the flight data to help develop a model for the system that I actually had, which would have given me a better valued transfer function for the physical system, for the frame, for the drag from the flight data. So also finding out about PIDs in the first place and how much they are used everywhere and how many different components make up their theory, that would definitely be something that I would like to do some further research into, as they seem to be a very popular and robust solution to instability and into controlling systems. And with that, that concludes my presentation. I have made great use of plenty of references, so if you are interested again in the embedded systems portion of this project, feel free to take a look at the link in presentation below. And other than that, I hope you have enjoyed this presentation, and thanks for watching.